Okay.
Okay, so we studied the force of impact of a metal ball on water. And so our purpose was to study a relationship between impact velocity and force felt impacts.
Our hypothesis was as the velocity of the object hitting the water increased, the force of impact on the water would start to act more like the force of impact on a solid. So we were expecting a nonlinear correlation between the force of impact and the impact velocity on water, so that it would be increasing more than force of impact on the solid. So hopefully at some point they would be the same.
So this is our setup. As you see here, this is the force plate, and we had a meter stick where we dropped it at each height. And we also had this foam on the force plate because we were worried that it would damage the force plate because it's like this solid metal sphere. And then over there we put a jug of water and and then we started measuring from the height of the water.
So we had the force plate connected to LogaPro, and we would drop the ball from 10 centimeters, 20 centimeters, 30 centimeters, up until 70 centimeters. And without water, we just dropped on the force plate and recorded force versus time. And then when we had the water, we dropped it from 10 centimeters above the surface, because we were comparing the force of impact on the surface of the water, not like the bottom with the acid water. So, yeah.
And so on the next slide is just going to be graphs. And the first peak of each graph is what we used for max force. We used the top of the peak. And so for impacting just the force plate, that was just the highest one, was the first one. But for water, there was a short one. I can just go to the next one. For water, there was this short one, and then the big one, the short one, was it impacting the water, and then the tallest one was it hitting the bottom. And we also took the area underneath these peaks, and that is the impulse, which is force times delta t, and that's equal to change in momentum.
So first we made these graphs of we had a graph of max force versus impact velocity to try to see if there's a correlation. The slope of this graph doesn't really have a real meaning, but we're trying to see if there was a linear and nonlinear correlation, and it's pretty linear. The correlation on this one is like 99, and this one is 96. So it seems linear, but I think we need more data to really see what the correlation could be. But like here, the blue is impact on water, and the red is impact on the solid. And I got impact velocity by doing kinematics from the height of the drop. And this one has a smaller slope because the impact of the force on the water, the impact force on the water was going up by less compared to on the solid.
And then these graphs over here was impulse versus impact velocity. And since impulse is equal to momentum, well, change in momentum, when you have change in momentum, change in momentum is mass times velocity. So plotting impulse versus impact velocity, the slope should be mass, and that's what we used for error calculation.
So to try to get a correlation between the impact velocity and the impact force, our graph didn't really show something that was nonlinear, so I tried making a ratio of the force of impact on the water over the force of impact on the solid, because if the water was increasing more than the solid was increasing, then your ratio would get bigger. And so it gets a little bit bigger, like here it's 0.03 and it gets up to 0.11, but at the end it stops kind of increasing. It's also a really small increase. So I don't really know if this shows a nonlinear correlation, but we will need more data.
Yeah, so if we had more data, then we could see if the ratio approached 1, which means that the water would act like a solid at 1. And so here was that error, and so this is what we did, like I said before, impulses change momentum, so the graph of impulse versus velocity, the slope would be equal to mass. And so there was a lot, here's the percent error, there was a lot more error without water. And this made sense because the force plate, the impact on the force plate, happened in a much smaller window of time, and so the force plate didn't have as much time to record data, if that makes sense. And there was also error from air resistance because we didn't factor that into how fast the ball was going, but it impacted.
So I feel like we didn't really prove our hypothesis or deny it. Our first graph gave us a linear correlation between impact velocity and impact force. But the ratio that I made of the force on water to force on solid shows an increase, and maybe that ratio would start to approach 1, but we need more data to see if that would happen. And then we mostly just had too small of a scale because we were still under 1 meter of drop. So we need to do more experiments to go from higher heights to get more data.
And we were worried about trying to go from higher than 1 meter on the force plate, risk of damaging the force plate, especially if it was a new force plate.
Yeah.
Thank you.
Holy crap, I just
Questions? Tell me about after the ball hit the force plate. What did it look like?
Well, yeah. So just on the force plate, the ball bounced a bit, and so the graph actually shows these peaks, which I assume are the different bounces.
And then the troughs are, so it pushed down the force plate, and then when it bounced back up, the force plate went up and read a negative force.
So you can analyze the force plate as a mass on a spring itself. So there's another larger peak. It seems to repeat. Are you sure that that's not the bounce? Maybe the second bounce.
This one?
So that one, those could be shaking of the force plate. That one is the one that really troubles me. Is that characteristic present in all the experiments? I mean, minus the water, obviously.
It actually is present in the water. But I don't remember if that was because we put our hand in the water and I didn't stop recording.
Yeah. The other interesting about the water is here we have this, it's pretty small, but here there's the first peak of it hitting the water. But then it goes back down, but not to 0. And we think that's because it pushes the ball pushes the water down, kind of, but then the water sloshes a bunch, and so they kind of mess with
And then
stuff.
with this one, the ball doesn't bounce in the water. It does like a little teensy bit, but it basically hits and stops. So this is the oscillation of the water, having waves because of the ball disturbing the surface.
Oh my gosh, that's another lab right there.
Yeah.
Oh my gosh. But here's my big concern. I think you assumed that the momentum was entirely lost upon the collision. But if you're telling me that it bounces, and if it bounces at all significantly, then the momentum loss might have been even more than the momentum incoming. So that's a concern. And that would really improve your error.
Okay.
If you consider that. You need to know how fast it bounced. Any more questions? Cool. Thanks, guys.